we have been covering certain important topics on probability theory, and I have given some programming using Python libraries for various distribution functions and some real life examples on the probability theory. And I tried to interconnect how probability distribution functions like the PMA, probability mass function, probability density function, cumulative distribution function. Uh, so these are important things. And also we have defined random variable and various types of random variable, discrete random variable and continuous random variable, and why they are so important in quantum computing. And so the notion of continuous random variable with the physical process, like how a quantum system interact with the environment, or how you are applying a control mechanism to the information processing via qubit, and that is a continuous process, continuous interaction. And what we observe through measurement is basically a discrete part, and we have seen certain distribution for that, like the binomial distribution and all. So today we'll take 3 hours class, and I'll try to, although this module in QT-03, in QT-03 we are covering something on the probability theory, statistics, statistical inference, then the various kind of estimation techniques, then hypothesis testing. So these are individually one subject at master's level. Okay. So and then basically some of the basically applications, right? So quantum computing is not explicitly mentioned in the syllabus. However, because we are covering quantum technology as a course here, so we'll try to connect them. So I have improvised today's class into 3 parts. So first 1 hour we'll be covering some uh, formal way of noise representation. So noise, we have understood from that yesterday class that the noise we can describe better with the probability theory, and what this noise means today I'll explain a bit. Okay, somebody is asking, can you brief the last class then? So then there is a lot of things done yesterday. So I'll be sharing all the notes today, although the notes I will be providing through Professor Pillai is a bit different than what I taught yesterday. I think there is a bit mismatch between because there is some different materials I'll be providing, some more materials providing as a part of notes. So please have a look, and please revisit this lecture, recorded lecture, so if possible. So a formal way of noise representation in the quantum system, although this is more related to the quantum information theory, but I will not cover quantum information theory in the QT-02 module. I have taken the quantum information theory a bit on the Krauss operator setup and all, but today I'll connect this noise with the probability theory, because we are covering this aspect. So this is much more fundamental and basic aspects. Then this is the first part of this class, and the secondly we'll try to cover, because statistical inference theory, there are a lot of things and it is not possible to cover everything. So I'll go through the statistical inference through some Python programming, some hands-on, assuming that you have some knowledge. If you do not have, I will be sharing sufficient material, but this might not be very suitable for the UG student, statistical inference. So this is a pretty advanced topic. So those who are in the final year UG, so mainly final year UG, or the PG or the research scholar. So for them it is a suitable topic, but for the undergraduate first year, second year, it might seem a bit difficult, inference theory. But I'll cover some overview of the things. So I'll try to represent them in a more something like graphical or visualization way, such that the overall objective is fulfilled. Okay. And then basically there are multiple inference techniques, and among various important techniques, some of the most important techniques are the least square technique. I'll cover how the least square is formed, one from the linear algebra perspective that we covered in the last week class. From linear algebra, what do we mean by least square for the systems for which we cannot find the solution directly, the inverse solution. Today we'll again revisit least square formulation from probability theory in a bit different way. And there are other two important statistical inference algorithm, ML algorithm, that is called the maximum likelihood algorithm. Maximum likelihood. Sometimes people use log likelihood function for that as well. So MLL or something like that. Yeah. And then there is map estimator, maximum maximum this posterior probability distribution based estimation techniques. So map estimator. There are several other estimator like MMSE, Kalman filter, and various other things, but these are beyond the syllabus. So we'll stick to the least square formulation mainly, and I'll give an overview, a detailed overview of least square, which is going with the QT-03 syllabus, and maybe in some other QT, maybe in QT 5 or 6, if I come back, or somebody else can take this topic in more detail, like ML or map. So this is a pretty much advanced topic. And then in the third part of this class, we'll do some more examples and some notion of quantum random number generator if time permits. If does not, I'll at least tell the concept of quantum random numbers. And then we'll do one error correcting code, one very basic error correcting code. Although I'm not an person, or I'm not an expert in this area, but this has some relation with this course. So probability theory. So we'll see that how to do that thing as an application of this chapter. Okay, so let's go ahead with this one by one. And between 1, 2, and 3, there will be 5 to 10 minutes of gap. So if you stuck with any question, please feel free to type in the chat, and I'll take care. Okay, why it is not moving? So there is some time issue with this board, even if that. Yeah. Sometimes there are technical glitches for which it does not work. Okay, so let's start with what we'll start today is quantum information from two terms. One is called noise, and another thing will be studied here. So very new. Those who are expert in quantum information theory, for them this is a very basic lesson. But just to cover the like overall audience of this course QT-03, I'm still covering the basic things because this is important for understanding for various things, like especially those who will program. So it is not just important that there is a problem P, you apply a quantum algorithm on the problem and you get a solution S, and you are so happy. This is not the case. But in this solution, if there is any error, S plus E, you have to quantify what is this error, what does this error means, and what is the guarantee of the solution is. Okay. So that's why this basic information is important. Okay. So we'll study two things, noise and operations, or the quantum operations. And there is a formal definition of what quantum operations means. Those who wants to take notes, they can. I am going a bit slow, but those who does not want to take, they can take a screenshot of this. Okay. So first is no practical quantum system No practical quantum system, for example, a quantum computer, is a perfectly closed system. And there are uh, unwanted interactions. So if there is unwanted interaction, there is something unwanted, and that's what we call, and that particular phenomena will shows up noise, unwanted phenomena, right? I mean, there is some uncertainty in the description of the system, and that will appear in the quantum information. So for this class, by information, I mean the quantum state. Okay. How you define quantum state is some probability with associated basis K0, and some probability amplitude with associated basis K1, where alpha square and beta square are the probabilities for the states K0 and K1. So by this I mean the information. Classical information, you just need to the bit string 0 and 1 and the associated probability of those bit string, right? But here we'll be learning more things other than this just 0, 1 and probability. So obviously 1 is here, instead of 0 and 1, you have the computational basis K0, K1 and the string of that. Then the associated probability alpha and beta, okay, and the set of that, they can take a lot of values where alpha and beta are the entire complex set, okay, scalar. And also not only we'll have one probability, there are multiple such probability cases, and we'll formally define them with the density operator formalism, which we have seen in QT-03, but here we'll see much more basic version of that. Okay, so why these things happens is that basically let's take some example to understand these things what I said. So suppose if a state of a qubit is represented by two positions of an electron, then that electron will interact and or may interact with other charged particle. Okay, so suppose you want to represent a quantum system using the position, this particular position and this particular position, and there is uncertainty of these positions of that electron, right? Okay, suppose this is the electron and this is roaming around this thing, and these are two particular position x1 and x2. Okay, and this x1 and x2 somehow you define as a in a computational basis K0 and K1 or something. In other ways also they can be some arbitrary quantum state. Okay, and there is some probability that the electron will be in superposition of these two known basis sets. Some probability of this plus some probability of this. Now this electron can interact with other particles. So there is some other particle and it has some charge q, and there might be some interactions, right? So it may be always some case where you have no control on this other particle, no control on the charge q1. Okay, because it is coming from the environment, and some of this system of this electron is not totally isolated. So if it is fine, like it is a totally isolated equation, then it is fine to describe by I del t of the wave function of this particular electron, say di equals to hi. This is sufficient to describe this particular phenomena. This is the solution of the Schrodinger equation. This is the Schrodinger equation. If you solve it, you will get E psi equals to H psi. That is other case. But I mean, this is the dynamic representation of this closed system. But there are always the case where your system is not properly isolated. It has some interaction with the environment or something, some other particles, which is unwanted, uncontrolled. Okay, and whose dynamics we wish to neglect. We are interested to with the dynamics of the electron, but not with the dynamics of the other particles, say P1. And its dynamics is not important to us. Okay, so this is the source of noise. So that will create an interference in this particular description of this quantum system, whose wave function is get psi. Okay, so with this, let us connect classical noise first, and then we'll go little bit with some distribution and other things, how this is important and how it affects the measurement and all will come. So first is, let's study the classical noise and the stochastic process. Classical noise, stochastic process, and specifically one very special type of the stochastic process is called the Markov process. So they themselves are, I mean, may take say a series of courses or series of classes, but we'll just see the overview what this means. Okay. So suppose I generate some qubits in a physical hardware. Okay. And I represent the probabilities. Okay. At the initial stage, say I have two information, 0 and 1. Okay. So classically, what can happen? 0 can stay with the probability that it is interacting with the environment. The generation of G is interacting with the environment. So the probability that 0 will be 0 after certain times is P, and probability that 0 can change to the state 1 where is 1 minus P, and this is again P, and this is again 1 minus P. So this is like this transition is P and this is 1 minus P, right? And assume that the generation of the probability 0 and 1 in the initial state is P0 for 0. The probability of generating 0 or the distribution of 0 is P0. Associated probability is P0, and the associated probability for the generation of 1 is P1, right? And this is the initial probabilities. So this channel is very common in classical communication theory. This is known as binary symmetric channel. Okay. So initial probabilities, and suppose after the effect of noise, your probability state changes to Q0 to Q0 and Q1. Okay. So started the generation of 0 and 1 as P0, P1, and after noise impacted here. So due to noise, this is due to noise, that 0 state will remain in 0 is probability P. 0 state can change to 1 with probability 1 minus P. And the evolved state, like the evolved probabilities, are Q0 and Q1. So which are the probabilities after noise has occurred. If this is the case, and so this is a if you have several such bit string, not only 0 and 1, so this can be multiple such bit string, and there is a set of probabilities, and that will give you the probability mass function of all possible bit string. If 0 and 1 are the random variable, okay, because there is randomness with 0 and 1, and the associated probability for 0, that is the x1 random variable, is p0, and x2 random variable, that is 1, the probability is p1. Then this is a probability mass function pmf that we have seen yesterday. And after the effect of noise, you have another probability mass function of the that is giving you the discrete distribution, basically, or the mass function more specifically, of all the random variables or the bit string where there is randomness associated. So this is the change of the probability amplitudes, and you stack them all as a vector quantity, p0, p1, q0, q1. So what you can write is that the evolved state vector q vector is basically this is some matrix E times the vector p. Okay, where q vector is the vector or the set of values from the probability mass function or the amplitudes probabilities, basically. There is a set of probabilities that is forming the vector q equals to some matrix, this matrix times the initial vector p, which is the probability of P0, P1, and all associated with the random variables 0 and 1. So there are questions, right? What are P0? Number of distribution? No, P0 is the probability of the random variable 0. Okay. So at the generation stage before applying noise. If you remove this P0, P1, that means your initial state 0 and 1 is deterministic. That it has equal probabilities. Okay. But if you want to keep the probability, still there is a generation probability. Say, for example, I should not introduce quantum here. I'll come later. But so initially you have prepared a quantum state as alpha ket 0 plus beta ket 1, right? So your basically initial probability is alpha square beta square, right? And there is impact of noise. Okay, some noise is acting there. And after the noise, you have suppose the distribution is alpha 1 square and beta 1 square, something like that. Okay. Then the second question is, and if a distribution, and if it is a distribution, then how can you represent it in a vector? Yes, that is what I am explaining. Um, so, so you have a random variable. Okay, so yesterday we explained this in, I mean, much detailed way, but still I'm repeating. Suppose you have a random variable x, and the random variable has certain symbols x1, x2, x3, x4. Okay. Uh, and classically they can be -1, 0, I mean 1, 2, 3, 4, or whatever it is, some experiment. Okay, if it is a coin toss experiment, it is head and tail. If it is some other experiment like tossing a die, there will be 6 random variables, right? When we map the events to the real number set R. Okay, that is how the abstract space to real number set, how we define the random variable. And there is the associated probabilities, right? That this random variable has the probability p1, it has probability p2, it has probability p3, it has probability p4, and you stack them as a column vector, and you call it as a vector, uh, say p vector. Okay, so this is your initial probability, say, right? And after noise impact there. Okay, so because you are now working with the quantum system, even in your initial state you do not know that 0 and 1 are deterministic. They are the, your quantum state is basically a distribution of 0 and 1 with some probabilities, right? And this distribution, suppose this probability amplitude of associated random variables x1, x2, and x3 and x4 change to q1, q2, q3, and q4, and you take it as a column vector as q vector. Okay, I mean, this is not the way how it is taught. Okay, I mean, I will be interchangeably using vectors, matrices, probability amplitudes, operators. They are highly linked, but that is not. It is how it is written in book. Okay. Also, I'll show something where a matrix, where the elements of the matrix are coming from some random distribution, and that particular matrix is called a random matrix. Okay, so these are advanced, like especially in the linear algebra and matrix theory, advanced courses. But I think these are important here as well. So I am covering some of the parts. But yeah, I mean, I'm fine to answer these questions. So now your what is this E? So basically, what is Q? Q is the evolved distribution of probabilities. Like the after the noise impacted, your probability amplitudes becomes 0 and 1, and this is some matrix, and your initial probability was P0 and P1, right? This was the case. This was the initial stage, and this is the final stage. Now I put the values 1 minus P, 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 and 1 minus P. So if it is P0, P1, these are the probabilities, okay? And probabilities of 0 and 1 basically, right? So what is happening here is that, so how Q0 is achieved? So if your, it is basically 1 minus P times P0 plus P into P1, right? This is the case. So if you see the picture above, so I have done nothing. So what I have done, just I picked up the values from the previous thing here. You just check between this figure and see this one. So 0 is changed to 1, right? With probability 1 minus P. That's why this element 1 minus P. 0 is changed to 0 with probability P. This is the P. Okay. So this is called the transition probabilities. Okay. How a state is transition from one to another, right? And instead of 0 and 1, we are associating how the probability has evolved. Okay. Similarly, 1, say this Q1 is the associated probability for the state 1, right? So it is evolved as Q1 with probability p to 1. So this is the p, and 1 minus p with the state p0, p1, right? So so then this is a matrix representation where all individual 1 minus p, and this thing we can represent as a linear equation. How noise impact in a classical system? It's basically a linear equation. And the linear equation um, is your evolved noise distribution, or the basically the vector whose component are the probabilities of a set of random variables. Q is a transition matrix, how the transition happens, and the initial probability vector. Okay. E. So now, if this is the case, then there are certain things. This E is called the matrix of transition probabilities. Matrix of transition probabilities. I will show examples and some programs also, don't worry, to make it as possible to visualize things. And the second thing is called the evolution. So either I can say the matrix of transition probabilities, it has another name called evolution matrix. Evolution matrix. And so what are the things is that what we can say from here, because it is a transition probability. So if Eij is an element of E, right? I mean, it is an element of this matrix. Then Eij, that is I is row and j is column position. So Eij is some position. It has to be either greater or equals to 0, right? Because probability cannot be negative by definition, by postulate, and it is greater or equals to 0, right? And also there is another thing. This is called the positivity property. And the second thing is that column sum summing to 1. This is called the completeness property. So completeness property is there in classical as well. I mean, it is not the case that completeness is there with the quantum theory, but completeness is there with the classical probability theory as well. So what is happening if you see across the column? So what is the column sum? 1 minus p plus p. So 1. So here also, if you see p plus 1 minus p equals to 1. So column sum will be 1. And individually, these all elements are the probability. So they should be greater or equals to 0. Okay. So these are two conditions for E. Now, what are the other things? So of course, this Q vector equals to matrix time the P vector. This is a linear equation that relates the transition of a system under the act of noise. So that relates the transition of a system under the influence of noise. So that is why linear system is so important. And last week we have taken how to solve linear system as well. So algorithm part is not difficult if you understand the basic how it is the problem is formulated. Solution is standard. Okay. So transition of a system under the influence of noise. So this is just I have shown for 0 and 1. But this linear equation will be echoed in the description of quantum noise as well, where the source of noise will be from the quantum system. But the probability distribution, now the probability distribution are encoded in vectors, right? So these P and Q are the vectors which encodes the probabilities, noise vector, right? We call them as noise vector. In quantum system, we'll be replacing them by something called a density matrix. A matrix with probability amplitudes, some values will be there, okay? And that will express the behavior of noise in the operator form. So I'll come the details of this. So before that, I have to define what a Markov system is and why it is important both in classical and quantum. Why we take the assumption. Suppose we have classical system and the classical information. Suppose classical information is C0. Initial set of classical information C0, that is a bit string of 0 and 1, some n bit string, okay, 0011, something like that, okay. And you apply certain gates, okay. Suppose gate 1, it may be classical, say NOT gate, for example. You apply a NOT gate here, okay, gate 1. You apply a gate 2. You apply a gate 3. You apply 3 quantum gates or 3 classical gates, whatever it is. The first gate I am calling it as a X, second gate I am calling as Y, and Z is a Z gate. So there are 3 gates applied on the classical information set C0 to perform certain operation on the bit string to get the modified bit string, right? And that particular bit string says CF, final bit string 0 and 1. So this is what we get. So both input and output are classical in this case. Okay. And suppose X, Y, Z are noisy. So these are noisy gates. So what we can assume is that this is an assumption, first of all, because N1, N2, and N3, I mean the gate 1, gate 2, and gate 3, of course, each gate is individually may have some noise distribution, which we don't know actually. The actual distribution we don't know, right? But what we and they are following some stochastic process. So let's define a process first. What is a process? How to define a process? So we have learned what is a random variable is, right? So that is some x, right? And x takes values from the set, say from the set x1, x2, some xn, right? Um, and if this process x is a function of time, like we can denote it as x of t, that these values x1, x2, x3, x4 up to xn, they are also function of time. That means xt you can now denote as a set x1 of time t, x2 time t, up to dot 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 xn time t. Okay, and their values can change over time. Then we say this is a process. More specifically, a random process, okay, or a stochastic process. Now, depending on the behavior of x1 with respect to time t, x2 with respect to time t, and so on, there are various types of process such as stationary process, non-stationary process. Okay, so I'm not going to that direction. Stationary, non-stationary. I'm just giving you the names. Wide sense stationary. Okay, weak sense stationary. So there are several definition, okay, of the process. So I'm not going to that part. One of that process is a Markov process. I am going to that particular assumption. When I say that a process, so individually you have a suppose some random distribution is coming from gate 1, and that particular thing you are saying, okay, random variable x1, gate 2, random variable x2, random variable x3, and they are all function of time, say t1, say t2, or same time also you can take t3, okay. And now you are looking at the process as a whole, as a composite system. Then what will be the effect, noise effect on the uh, output set of string, classical bit string? Okay, right. So a reasonable assumption is that the noise acting on X is independent of Y. So let me write the sentence maybe for the clarity. This is important. A reasonable assumption is that So this is a very special type of noise where you assume that if a system input is I, output is O, and pass through multiple systems, say X, Y, and Z, which create some noise behavior. Each quantum gates or each classical gate has some noise, right? Some noise level, and you assume that the noise acting on X, this particular gate, has no is independent how the noise is acting on Y and G, and so on. Like how the noise is acting on G, it has no relation. It is independent of X and Y. If this is the assumption you take, then basically this particular special type of stochastic process is called a Markov process. And the most important word here is the independent. Okay. So that means when noise is acting here, say N2 noise is acting here, N1 noise is acting here, N3 noise is acting here, and there is no correlation between N2 to N1, N3 to N2, so they are all independently generated. Okay. So, okay, there is question. Oh, it's now coming. Okay, so am I audible, right? Or any voice issue is there? Let me know. Okay, thanks. Hmm. So, so that means the generation of N2 has no memory effect of N1. So this is, I'm telling the word memory effect, although this word is not written many places, but this is important. No memory effect, okay, of the generation of N2 with the N1, or no correlation, of course, okay. So then that's that particular process of noise, how it impact the information. This is a special type of the stochastic process, and we call them as a Markov process. And hence, a classical noise process involving multiple stages of the system or multiple gate operations are described by the Markov process, assuming noise is caused by independent environments. Okay, this is a very strong assumption. That's why those who are interested, and also those from the physics background, they know that in open quantum system also, like that is a very specialized branch of quantum theory, they also consider in certain cases as a Markovian noise, where various quantum sources of noise are not correlated. So Markovian noise process for the quantum system as well. So this is the same process which is assumed in classically, but actually in quantum system, maybe there is memory effect, like the N2 has some correlation with N1 because the environment is same for Y2 and environment is same for X1. But classically, you are assuming the environment is different for X and Y. So that may be the case for non-Markovian system, but that is a much complicated part. But we'll stick to this process, Markov process. Okay. Okay, so one question. Does this rule sustain even during superposition state, since the uh, quants will be coherence? No, quantum system, in general practical system, this assumption does not work, but this assumption we take just for the simplification of our calculation. Otherwise, you have to take joint probabilities of individual system and then you have to calculate. Okay, so there is probability law for that as well, if it is correlated. So mathematical tool is always there to help, but whether it is easy way to represent or not, or a viable way of represent or not, that is a separate question. If they are entangled, yeah, these are some good questions. I do not know the answer, so please have a look in that site. Okay, so now I'll introduce something very special that is called the quantum operation. Any other question, please feel free to type. Okay, so maybe all the question, it is not, I mean, I may not answer all the question, but it is good to know the question. Okay, so what are the books I have? I haven't referred books, right? So please have a look with two books at least. One with Quantum Computing and Quantum Information by Nelson Chuang, and Quantum Information Theory by Weil. So these two books are very important, but for UG level, it might be a bit difficult. But I mean, the basics part can be taught in the UG level. but there are many advanced theories of quantum information theory in these books, so that may be reused. So a general tool for describing the evolution of quantum systems, like the classical system we have seen, used in many circumstances, including the stochastic changes to the quantum state. So this is a general tool for that. And let's do some equivalence to the classical part. So classical noise, typically we represent classical noise states or classical state with noise. We typically represent with vector of probabilities or the probability vectors. Right. Okay. So those who typically work in the electronics communication theory or control system, they know that if your system has some input X, it passed through some communication channel, say some H, and you get some equation Y equals to HX. Now, if noise acts here some W, then you have the equation HX plus W, and this ultimately impact this the values of this Y. Then the set of values in X is basically some X0 to up to Xn minus 1, and this should be also Y0 to Yn minus 1, where Y you are assuming that X0 to Xn minus 1 is noiseless, and Y0 to Yn minus 1 is noisy, right? Noisy observations data and at the receiver end in the communication channel. But still, you just see that this state is just simply a vector with noise states, and this is a set of vectors without noise. But still, in the generation, still there are certain noise from the quantization noise and other things are introduced in the symbols. Okay. So, I mean, whether you assume or not, that's a different thing, but it is there in the classical system as well. Okay. So, so classical state, we normally we represent the vector of probabilities, noisy state. Basically, I should say classical noisy states. Okay. And quantum noisy states, basically, or the quantum states, or the quantum noisy states will be represented with the formalism called the density matrices. And we'll be representing these matrices by rho. Okay, I'll define this term and then I'll give a break of 5-10 minutes. Okay, so so let's many of the people who are very new to quantum information part. So for them, I need to define this term. For others, I think this is very simple. So let's see some background on this, why this is important. So instead of so you are trying to generate a quantum state, right? And that quantum state is alpha ket 0 plus beta ket 1. But there is a physical hardware that creates this superconducting qubit or whatever qubit it is. Suppose you create an artificial atom, and this is the ground state, and this is the first excited state of that particular artificial atom, and you are calling this ground state at ket 0 and the first excited state at ket 1, and then basically you are trying to control, you are creating a superposition state of this or a like a combination, linear combination of these two particular state, that is some state ket psi, which is basically some with the probability alpha square to be in the state 0 and probability of beta square to be in the state 1. But what is there a practical hardware that can create 100% with surety that this particular state is alpha state 1? There is a 100% surety about the alpha square and beta square. So there is always like because there are physical interaction with the environment, and it is never a possibility to create an full isolated system. So if it is not isolated, then it will basically your quantum system will interact with the environment, right? With certain amount, like certain degree of freedom, right? And then there will be noise introduced. Say for example, in thermodynamics also, even certain cases like there is some heat transfer. So this is in temperature T1 quantum system, and your environment is at temperature T2, and there will be some interaction change of heat, right? and the system, the joint system will try to come into the thermodynamically in equilibrium, right, by the exchange of heat. This is the general nature of system, whether it is quantum system or whatever system it is. But as soon as this system is not isolated quantum system and it interacts with the environment, at least there might be some sort of interaction. It may be magnetic interaction, it may be thermal interactions like this, the exchange of heat and all, for which you have some uncertainty that will act on the state psi. And instead of this psi, what you will be generating is some psi I. Okay. So at every instant there is some uncertainty with the alpha and beta, right? So so basically your quantum state is basically an ensemble of states. Ensemble of states. So that means, what do I mean by ensemble of states? Is basically if you create a qubit, so for I equals to some numbers, okay, say psi 1, psi 2, psi 3, psi 4 and all, and then basically there is a collection of such states which are known as the ensemble of the quantum states, okay, and that is basically psi I, and many such psi I. Like first time you create some psi 1, psi 2, so every time you have a change in the probability amplitudes alpha and beta. Okay, this is the case. So given a state of a quantum system which not completely known, okay, and suppose a quantum system is one of the number of states of psi I, where I is an index with respect to the probability. Now every time you create some psi I, that psi I is also random, right? And that has also that has some associated probability pi. If that is the case, then we can represent a set of ensembles for pure states. That the pure state is basically pi and psi I, where I suppose I equals to 1. So you have the psi 1, the first quantum state with probability p1, right? And the similarly you get another quantum state psi 2 and p2. So you repeat the experiments many times. So how many times you get the state psi 1, how many times you get the state psi 2 and all. From there you will get a probability set of probabilities, and you define a state with some probability and the associated states. Okay, so this is the basically way of representing the ensembles of quantum states. So now if this is the case, so then we define something, and that something is called a density operator. And the density operator of the system, because generation of qubit, where qubit itself is a vector, and that has some uncertainty of generation with probability. Okay, that's a discrete random variable. And then we define a matrix rho as sum over all such I observations, EI, state psi I, outer product with psi I. This is important. This is a matrix outer product. Matrix outer product. Okay. So so basically, if you have a vector secant x, so this is the dot product of x and x. This is called the inner product. And if you do x, this is called the outer product. Outer product. So this is often a projector operator. So if it is say 0, 0 is the state, so 0 and 0. Okay, if this is the case, so dot product between 0 and 0 we have seen yesterday, that is equals to 1, right? Because this is the same unit vector. And outer product of 0 and 0 is the projector operator or the projection operator. And that is the generalization of this is psi I and psi I, because psi is basically a superposition state of 0 and 1. So you can denote in this way as the outer product of general state vector. Okay, and the associated probability. This is just the definition of density matrix, and we'll come with how this density matrix works and various other properties. So let me discuss one or two and then I'll give a break. Okay, so there is a question. Okay, can noise cause the ensemble of states to be not normalized states? Do still they remain a valid quantum states? Very good question. Yes. I should say yes, because So there are specialized branch for this, especially if it is an open quantum system. So there is illegal quantum state, and if there is illegal quantum state, so how to act on them. So there are process tomography and other special techniques and tools for that, but I'm not going to that direction. I'll stick to certain assumptions, and that will define various properties of this flow. But you are actually correct, so that maybe reality it may happen. So suppose we have a quantum state psi I, and it evolves with u. U is the time evolution operator. Okay. So suppose we get a state, say state y from the state, okay, from the state psi I to yi, and definitely yi will be u times psi I from time evolution equation, right? Unitary times this from Schrodinger equation. And suppose this happens with probability, suppose the probability of initial probability equals to pi for this state, pi for psi I. This is the initial probability for generating the quantum state I. So now the evolution of the density operator. So this is the state representation of the quantum system, right? Then the evolution operator we have defined as sum over I, which is a probability times the outer product. Outer product means psi I and psi I. Okay, many might have confusion. What is these things? Okay, let me okay, define this. What is this? Although you haven't asked me, but I understand that it might be a question to many. Okay, so this is what? This is your okay, let's take realistic value. Say square root 3 by 4 ket 0 plus square root 1 by 4 ket 1. This is suppose a quantum state. Okay. And the outer product is what? Outer product is basically psi, outer product with psi, right? And this is typically a vector, right? So the amplitude of this vector is what? The amplitude of this vector is basically square root 3 by 4 and square root 1 by 4, right? So this ket psi, you can write it as, it's a column vector, right? So it's a square root 3 by 4 and 1 by square root basically 4, right? This is the state, okay? And then basically outer product will be this particular vector times this. So I'm writing opposite. So let me write the correct part. So this example will clarify more. So the first part is a column vector, right? So column vector is square root 3 by 4 and 1 by square root 4. It's a column vector times the row vector. Row. This is a row vector, right? A square root 3 by 4 and square root 1 by 4. So what is the answer? So basically it's this time this. So the first element will be 3 by 4 and then this times this. So square root 3 by 4. Then this times this means square root 3 by 4 and this times this, so 1 by 4. So this is the matrix, right? So this is basically and this state is generated with some probability, say p1. Now next time again you generate this quantum state, this alpha beta will change, right? Again you will get some other matrix. So if you get such various such matrices where this generation of this matrix, and what are these values? These are the probabilities values, right? Probability amplitudes coming from the probability amplitudes, right? So these are the probability values of a matrix. Now they are the element of the matrix, and that matrix we are calling as a pure state density matrix, right? And this pure state density matrix, it happens with the probability P1. Now, next time you have a different set of probability amplitudes alpha beta, and you have a separate matrix, different matrix here with probability P2. So every time you do, you have each probability P1, P2, P3, P4, and so on. Now, okay, if my calculation there is an error, I am sorry for that. So maybe I overlooked anything. So please, you can calculate it and check it whether the values are correct or not. Okay. So all such combination of the probability matrices, all the sum of those matrices times the probabilities of their occurrence, right? You get something, a new matrix that you are calling a matrix density matrix. So instead of this time evolution of a state, now you will do the time evolution of an operator. Okay. So I am applying the time evolution operator on top of this matrix row. Okay. And then basically what is happening is sum over I, ei, u times this state. So you just do what I'm doing is that, so you just apply this state here, right? If you have any confusion in this equation, just let me know. So there should not be any confusion in this equation. If you have any, just ask me. So what I have done, so if a state is psi, and if you get a evolved state, it's u psi, right? If this is the case, and if you define this rho as a probability times the outer product of this, so outer product of this will be what? Outer product of this will be u psi and u psi star. So that will be u psi this time this I mean this is the way of actually this part will come first and this will second, so it will be u. So and then basically the probability amplitude times this. Okay, this is the case, right? So if this is the equation, then this unitary evolution, time evolution is basically index free. There is no I in this, so it can go outside the outside this summation. So it will be something like this: pi psi I times psi I, and u dagger, and this is your initial row, right? So you will be row u dagger. So this is a I mean very common question. Even I hope this is this might be there in the MCQ questions as well. Any examinations you will face, this is a very common question. Okay. So suppose your initial random state is uh, some quantum density matrix. So this is your initial. Okay. And you apply a quantum Fourier transform on top of it. Okay, what will be the output state? So it will be TFT times the row initial times TFT dagger. This is the output state. Pivot state. Quantum Fourier transform. Simple thing. So you transpose your dagger out. So you always use this dagger sign. So transpose is not for the complex. So quantum everything is complex. So either you use Hermitian, but sometimes the Hermitian looks like edge matrix. That's why better to use either dagger side or star side. Okay, any one of this, not this one or T. Of course, there will be it won't be T. It will be dagger side, or you can use the star side. Okay, let's take a break for 5 to 10 minutes, and we'll come back to see some more properties, and then we'll go for some programming sessions. Yeah.